Hi, I'm Henri Devillez from UC Louvain, and I'm going to present our work titled Can we cast a ballot as intended and be receipt-free? So this is a joint work with my supervisors, Olivier Pereira and Thomas Peters, and also with Quentin Yang. So in this work, we study very general voting models with possibly many interactions. This is because we want to look at the limits of such kind of models. So we look at this kind of flow in which a voter, to cast a vote, interacts with a voting device and then in turn interacts with a casting server. From all these interactions, a ballot is computed and published on the bulletin boards. And when everyone has voted and all the ballots are on bulletin boards, then a set of talliers will compute the result of the elections from these ballots and publish it on the bulletin board along with some proof that the result has been computed correctly. And then finally, any voter can just check that this proof checks and that their ballot is indeed on the bulletin board. So when we run such kind of an elections, there are some properties that we want. This is a non-exhaustive list of security properties that we want. So first, there are some verifiable properties. So, for example, cast as intended. So when a voter is casting a vote and gets a ballot, then we want that this ballot indeed contains the vote of the voter. Following, there is the recorded as cast property. So when this ballot is recorded, we want that we do not change the content of the ballot and that the vote is still there. And then finally, we want that all the ballots are tallied and the result is indeed can be indeed explained as the tally of all the votes contained in the ballots that are recorded. So this is the verifiability properties that we want, but we also want to protect the privacy of the voters. And one way to see that is that we want that nobody could learn anything about the voting patterns of the voters except what can be learned from the result of the election. And this is all good, but we sometimes want something that is a bit stronger, such as the receipt freeness. So for this property, we want that a voter should not be able to produce a proof or a receipt of how they voted to someone else. And this is typically to avoid the voter to sell his vote to someone else. In this work, we focus on the cast as intended property and on the receipt freeness property. And this is because those two notions are difficult to achieve. And also the mechanism that are used to achieve them usually don't synergize well together. So in this work, we first extend receipt freeness definition to work in a setting with a lot of interactive ballot submissions. And then we also show that it is actually impossible to have cast as intended and a receipt freeness if there is no interaction during the whole process, which motivates our setting. And finally, we show in a more positive note that it is possible to build protocols that achieve those two properties if we have some interaction somewhere. So this can be an interactive voting process or through some interaction with a registration service. So to define receipt freeness in the interactive case, we take inspiration of the non-interactive case, for which the intuition is as follows. So there are two scenarios. So in the first scenarios, the adversary gives instructions to voters, and the voters follows these instructions. And then in the other scenario, the adversary still gives instructions to the voters, but now the voters try to deviate from these instructions and to cast ballots containing their own voting intentions. So we want this, for the protocol to be receipt-free, we want these two scenarios to be indistinguishable from the point of view of the adversary, which can also see all the verifiability proofs that are published on the bulletin board. And so a bit more formally, we can see receipt freeness as this. So the adversary gives an instruction as a ballot, a single message to be sent to the casting server, because we are looking at the non-interactive case first. And to escape this instruction, we also consider an additional algorithm, the deceive algorithm, that take as input the instruction, so the ballot, and the vote that should be casted. And so these deceiving algorithms output another ballot, another message to be sent to the casting server. And so we want these two scenarios to be indistinguishable for the receipt freeness, but we also want an additional property that is called deceiving correctness. And essentially, we want the deceiver algorithms to be relevant and to output a ballot that contains the voting input. And now, to extend receipt freeness to the interactive case, there are some considerations that we have to make. So first, since there are many interactions now between the voting device and the casting server, the instructions might want to adapt to these interactions and to these messages. And so we model these instructions as a Turing machine that take as input the state of the machine and also the last message that has been received, and sends in return, outputs in returns, the next message to be sent to the casting server. And when we define these Turing machines, we do not make any assumptions about its content. So the adversary could obfuscate it. And so the voter has no idea what is the strategy of these instructions. And finally, these instructions also outputs a transcript that is sent to the adversary. And this is because the adversary is not aware of the communications that the voter will receive from the server and might ask the voter then to record them and then to send them a transcript of the execution of the protocol. So we can put that into our boxes. So the main difference is this Turing machine that interacts with the casting server and which outputs in the end the transcript to the adversary. And then on the right, the deceiving algorithms now takes the instruction as an input and interacts with the casting server. So for the receipt freeness in the interactive case, we still want those two scenarios to be indistinguishable from the point of view of the adversary that has its view a bit augmented with this transcript now. Now we come to one of our main results, which is that it is impossible to have cast as intended and receipt freeness with a non-interactive submission process. And I try to give some intuition of these results. So we are going to assume that the voting process is receipt free, and we are going to show that it can then not be cast as intended. And so on these two boxes, you can see that as a cast as intended game. So on the left, we have a non-honest voting device. And then on the right, we have a malicious voting device that tries to vote for another vote V star. And so we can see the human voter, H, as a coercer that tries to give some instruction V to the voting device. And the voting device can then try to escape from these instructions and run the deceiving algorithms on this input and on V star. And so since we assume that the protocol is receipt free, the human cannot distinguish between the left and the right. It cannot distinguish between a non-honest voting device that does as it should and a voting device that is malicious and runs the deceiving algorithms. And so for this intuition to work, we also need that the deceiving algorithm is correct. So we want that V star indeed contains a vote that is V star. So in the paper, to formally prove this result, we use a unusual proof technique. So we build three adversaries, an adversary for the cast as intended game, an adversary for the receipt freeness game, and an adversary for the deceiving correctness game. And then we run these three adversaries in parallel, and they are built such that the building board that results from the execution of the voting protocol and the games. So this building board follows the same distribution in the three cases. And then we also show that the advantages of this adversary, so if you take their sum, it's at least equal to 1. So this means that at least one of them has an advantage that is bigger or equal to 1/3, and thus that at least one of them is winning with non-negligible probability. So this essentially proves our result. And then finally, we show that we can get those two properties. So we built three very different protocols that have case as intended and with freeness. So in the first protocol, we use a multi-round approach. So the voting device and the casting server runs many interactions together, but it has the advantage that it is human compatible, so to say. So by that, we mean that the human voter that interact in this protocol only needs to flip some coins and to compare strings between the voting device and the building boards. Then we also have a constant round protocol that only use 3 rounds of communications, but ask a bit more from the voter to do in the voting process. And those two protocols, they use very simple crypto primitives. So we need a CPA encryption scheme, we need also high commitment schemes, and finally we need a zero-knowledge debatable proofs that exist for any NP language. And then finally, we have a third protocol that use only a single pass submission process. But in turns, it also needs some interactions with a registration service before the start of the voting protocol. And this last protocol, it needs more involved crypto primitives. So we need a trunk and also some malleable non-interactive zero-knowledge proof system. And so now I'm going to explain a bit and give some intuition about our second protocol that use 3 rounds. So first, we use a technique that is quite common to build as receipt-free protocols. So to cast a vote V, we create shares of this vote, and we encrypt the 2 shares, V0 and V1, into 2 ciphertexts, V0 and V1, that we send to the casting server. Then this casting server re-randomizes the ciphertext by multiplying them with an encryption of 0 and publish these encryptions on the building boards. So from V0 prime and V1 prime, so we can reconstruct an encryption of the vote V. So this is receipt-free because the voter does not know the randomness that has been used to re-randomize the ciphertext. So it cannot give an explanation of an opening of the ciphertext published on the building board. But this is not verifiable yet. So in the second step, the voter also sends a commitment of random values, so alpha and beta, to the casting server. So the human voter computes this alpha and beta without giving them away to the voting device. And then the casting server replies in return the values that will be published on the building boards. This can be seen as a commitments on whatever will be published later. In the final round, the voters give the alpha and beta values to the voting device, and with the casting server, they compute an opening of the value p0 to the power alpha times p1 to the power beta. And this is published also on the building board. And then there is also some divertible proof that can be done in parallel to show that b0 times b1 is indeed a valid encryption of a valid vote. So now we'll see why this protocol is cast as intended. So first, a malicious voting device to cheat has to modify either v0 or v1, and this before knowing the alpha and beta values. So this is because b0 and b1 is committed to the voter before revealing the alpha and beta values. And so the voter, at the end of the protocol, is expecting to see v0 to the power alpha times v1 to the power beta on the building board, but if the voting device cheated and modified v0 or v1, then with very negligible probability, the v0 to the power alpha times v1 to the power beta that have been modified will be equal to what the voter is expecting to see. And then it's also receipt-free. And this is because of the re-randomization that refreshes the randomness, as I explained, but also it's not the end of the story, because we need to show that the voter can produce the ciphertext such that the opening done at the end of the protocol can be explained to the adversary. And this works because the voting device can first extract alpha and beta from the instructions given by the adversary, and this before the very first interaction of the protocol. And this is because the voting device can just simulate the instructions, get the alpha and beta, and then go on. And then we only need to find a secret shares V0 and V1 of V, of the vote that we want to cast, such that the linear combinations of this secret sharing with alpha and beta gives what the adversary is expecting. And this can be done by solving a linear system. So the protocol is also receipt-free. So in conclusion, we ask ourselves if we can achieve cast as intended and receipt-freeness properties. And we've seen that sometimes it is not possible, especially if we do not have any interactions in the voting protocol. But we've also shown through 3 different protocols that we can get those 2 properties. This either with some interactions in the submission process or through some trusted authorities with whom we interact before the voting protocol. So finally, I would like to say that we focused on feasibility results. But this opens the way to designing and finding new protocols that can achieve those 2 properties with more practical and more usable approaches, but also more efficient. So if you're interested in our work, you can find the full paper through this QR code, and thank you.